regardless, it's more fun live because you can ask questions. But yeah, for sure. Like if you want to go through the content more slowly, if you're busy, no, definitely try to make it convenient. I think most people watch the content on YouTube later. So, all right, I think we're that's okay. Let's do this. So welcome, folks. Like today, I'm going to be going over like this really excellent survey called a survey of generalization and deep learning. So this is a survey by like Robert Kirk, Amy Zhang, Edward Griffente, and Tim uh, Rocktashel. Sorry for butchering their names. Um, so, um, I mean, so yeah, I will say like if Amy's watching this, like shout out, like thank you for writing such a great paper. Um, and yeah, I mean, because like so Amy and I used to share a desk at UCSD. But regardless, like let's talk about the paper. So the paper is very interesting for multiple reasons. So let's just start going over it. Um, so basically, I mean, let's just go over like what it's doing. So the study of generalization, and we'll talk about what this term really means. So it aims to produce RL algorithms whose policies generalize well to unseen situations at deployment time. So the classic example here is something like you're trained on like you've trained a robot in kitchens, you want it to work well in living rooms, or you've trained a robot well in a simulation, you want it to work well in the real world. Within supervised learning, this is really just the way we do things, right? Like you have a training data set, you have a test data set, whereas in RL, the training and test data set tend to be the same. Um, so, which means that like often like RL algorithms like will be overfitting, they'll be brittle, and environments tend to be like diverse, dynamic, and unpredictable. Like there's sort of a one diversity is just this idea that there's just too much stuff going on in environment, like things change very quickly in chaotic ways. So this is, and then even then like there's events that you couldn't possibly predict. So think things like black swan events, where it's just like impossible for you to predict like what's going to happen. So this is a survey of this field, and they call it nascent, even though I'm not sure that's really true. Like it really felt to me like they were covering like old hard problems in this area and synthesizing them. So they're going to give you a state of the art of the work, and they're going to argue that specifically, let's just highlight this, a purely procedural content generation approach to RL is not conducive to progress and generalization. So there's been a couple of environments, so things like a mini hack that basically gives procedural generation on top of more complex environments like an attack. They're claiming that this doesn't work, and we're going to go over their argument why. And basically, a better path for RL would be uh, here online adaptation and tackling RL specific problems. And they're suggesting that we need to build benchmarks for these things because they don't exist, right? So just in terms of general themes, like let's just go over this. There's going to be like one, we're going to define what is generalization. We're going to basically discuss like environments in RL. So if you've watched like some of my past streams on Unity, you know this topic I'm super fascinated by. Like there's just like an incredible amount of stuff you could do with RL environments. So we'll discuss some of the most popular ones. 3, we're going to discuss like benchmarking. And 4, I guess we'll talk about, yeah, I guess this is 3, right? Like basically benchmarking, really the future of benchmarking in RL would be a better title here. All right, just like opening up chat. Okay. All right. So first off, like, I mean, the RL framework in of itself looks very much like this. Like you basically have like an agent that's acting in some environment, and then the agent basically takes a bunch of actions, and the environment gives you back like a new state. Basically, uh, how did the agent's action change the state, and maybe like a reward. Yo, hey sir, dies a lot. Nice to see you both. And James the Snake, thank you for both coming in. Oh wow, 5 viewers. Like, thank you, folks. Like, if you have any questions, like my streams tend to be very interactive. Like, I'm happy to explain any sort of basics. And what we're really going to be discussing today is this generalization survey and reinforcement learning. So this is sort of the general framework, like of RL, and there's not like I mean there's a lot of nuance to it, but for now like this will be sufficient to understand the paper. Um, so there's a couple of applications where it's used. So one is autonomous vehicles. There's robotics, right? There's also like gaming. I don't think they mention it here because maybe games in of themselves may or may not be interesting. Depends. I would really just add gaming as an application. And we need like RL algorithms that can be used in the real world. So what types of problems do RL frameworks excel in? Like a heuristic sign that needs simulators. Uh, yeah, I mean, so really like robotics and autonomous vehicles, because you can't run like an like a random policy on a real robot because it could actually hurt people, right? So you could, in principle, if it was controlled enough and its range of motions was limited, but it's just like not it's not super productive. Oh, that's really cool. Yeah, so maybe I'll give you like the Tesla example, right? So like let's say in Teslas, let's talk about Tesla for a second. So let's say you have like this car driving, right? So this is my car. So you're viewing it from the top. And then there's sort of like a turn here, right? So the car basically needs to do like a bunch of actions, like go up, 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 and then at some point maybe go right. Um, and so the agent will basically look at the current state. So it's going to aggregate like all the sensors in this area. So aggregate sensor data, and then basically predict like go like left or right. It's a bit more complicated because it's like an angle, so it's gonna maybe just like predict a single real value, which is like degree of turning, right? Something like that. So the nice thing about like Tesla's use case is that like, well, humans are actually driving this thing, right? So if a human sees this and they go to the right, you go great, like the label was right, right? Your label is equal go right, and you can do gradient descent and update your model. But like theoretically, it's sort of like the same, right? Like let's say even if you didn't have this label, the bot like or the car is in the situation and needs to figure out that going to the right is the best action. So unfortunately though, like a lot of environments for RL are fairly limiting. So there are things like Atari, like Mujoko. So Atari are literally like a bunch of Atari games. Mujoko is like a very popular physics simulator that was recently purchased by DeepMind. And they don't really have this ability, as in, at least natively, there is no distinction between test and train, even though some environments do add that like on top. And so, yeah, they do explicitly mention this is in stark difference to uh, supervised learning, where the training and testing policies are disjoint, right? So this means that like why do we even have training and testing data sets? It's to avoid overfitting, and this means that RL tends to be very prone to overfitting, which explains a lot of issues around like this is why it's sensitive to noise, this is why it's sensitive to the initial seed. Um, this is why if you adjust the environment even slightly, like the algorithms don't do well at all because they're overfitting. Like they're just learning the specifics of that specific environment as opposed to learning things. Oh, and they do mention the problems here with seeds, for example, in a whole bunch of papers, like 4 papers at least. Um, so really, I mean, if we look at this, um, they're then saying that there's actually like three different classes of environments. So like the first one is what they call like the singleton environment, which is your training and testing data set are the same. So like again, so here the example they give. So at the top here is Atari. Like let me zoom in a bit. So you can see all of these like different Atari games, and you would basically train on one game and test on the other. The other is like I mean is like Mujoko. So you have some sort of physics simulator, and then again you train on some simulator, and then you test on the exact same simulation. Uh, well, there's like slightly more interesting environments, like which they call the IID generalization environments. And so going over this, they're saying, well, the training distribution is equal to the test distribution. So what's the difference here? So the main example they go over is like really procedural generation here. So let's say that you learned how to play like a Mario level. Like theoretically, like you could make some random changes to this Mario level, and then the environment should still work. The agent should still pretty much just work. So a famous example is OpenAI ProcGen, but there's also the NetHack learning environment, and really not NetHack. So NetHack is a very complicated genre of games called a roguelike, and what that really means is that you're basically going through like some dungeon, and you're taking like a bunch of actions in this dungeon, and the dungeons tend to be very long, and then there tends to be like all sorts of weird secrets that let you break the game. So maybe I don't know if you find like an amulet So if you find like an amulet like way deep somewhere in a dungeon, it turns out like right before the final boss, you can show them the amulet and then they'll die in one shot if you have the holy arrow, right? So this is stuff that humans are good at because like we'll have wikis. I mean, individual humans aren't good at it. Communities of humans are because we can generate wikis. So this is really hard, and as far as I know, like most RL agents don't do well on NetHack. So one way to simplify NetHack is to create something like MiniHack, which is create very small environments that are randomly generated, and ideally progressively make them harder such that you can deal with NetHack. So this is what this means really, that the training distribution is equal to the testing distribution, even though the environments are not the same. And the last example is when the training and testing distribution are not the same. So this could be things like self-driving car simulators where the environment are really huge, causal world, which I've never heard of, but like or like basically some like control suites where you need to do different kinds of tasks. So okay, maybe you learn how to swing. Now like go learn how to run, right? So these tasks aren't like distinct in nature, but within environments they are. So how can we solve this? So I have two questions in chat. So what do you think is missing environment uh, in framework nowadays, like a niche that's not filled? Sure. I think what's really missing is two things. Like one is there's not enough environments that make it easy to basically progressively make them more difficult along various dimensions. So let's say you have an environment that tests out like some spatial reasoning skills, but also some language skills. How can you progressively make the environments like more difficult along those like spectrums to basically guide agents and not make the job too hard for them immediately? The other I would say is more of an aggregator problem. Like I think I would just really like a data set that basically picks a random environment out of all the environments that are available and gives the agent that or gives it random frames from that. So basically, just really making it difficult for it to overfit on a single environment. Um, and I would say like those are the two like main ones that I can think of. There's stuff like multi-agent or using MMOs, and I think actually no. So the third major one is I think we need an environment where it would be easier for humans to input like data such that you're not paying humans. So the thing is like back to this Tesla example here, right? Like Tesla isn't paying you to tell it whether to go left or right, right? So um and that's great, right? So if you make a game fun, for example, people may be willing to give you data for it. So you can imagine something like, let's say you have a Twitch stream running, and that this Twitch stream is like collecting like some data about like some about some game, and just by virtue of people playing it, like they're giving you helpful data to improve the algorithm. So how can you create like fun environments that encourage this sort of behavior? Tesla's self-driving cars is like one example of that, right? So these are the environments. Um, let's see here. Yeah. So basically, like remember when I was talking briefly about like basically just picking a random environment. So this is really what's called like zero shot policy transfer. So if I train you, for example, to play Mario really well, can you go play Space Invaders now, right? So the tasks are different, but at least anecdotally, like we know from observing, like I don't know, quote unquote gamers, that if you tend to be good at one game, like you're likely to become pretty good at other games. Like there's some transferable skill sets. Yeah, that's not really clearly encodable. Like it's not clear how you would describe the base skills. Like I don't know, maybe jumping and pushing buttons are skills, hand-eye coordination. But as far as I know, like I don't know if this really actually also really works really well. So they do mention like an explicit limitation is that they don't cover multi-agent reinforcement learning here, even though theoretically these aren't too different. So the difference with multi-agent RL is imagine like more of like a use case like Dota. So you have like 5 agents that are cooperating to beat like an enemy. The nice thing though about like games like Dota or like as far as I know, like in OpenAI in the OpenAI 5, what OpenAI did was they basically treated each agent as independent. So they each agent treated the other agents as just part of the environment, and that works fine. And so maybe you don't need them to communicate explicitly, or maybe you do. So an alternative. Oh hey Cas9, how's it going? So an alternative like and where multi-agent RL gets interesting is that agents can communicate like small messages to each other. So basically, let's say this is agent one, and then this is agent two, and then here you basically pass a message M1, and then 2 to 3 passes like a message like M3, M2, and then maybe this agent talks back. So if agents are also allowed to do these kinds of things, like what can they do? And communication can be implicit or explicit, right? Like maybe we can communicate just like with my mouse clicks, with like a bunch of button presses in the environment that don't do anything. Maybe it's explicitly something like a language model. So there's all sorts of ways you can encode language implicitly. Like it could be a code, or it could be an explicit like it could be an explicitly coded language, almost like protobufs. It could be something like is pre-trained, like the human language, or it could just be something that's like inferred from actions. Um, so really, the main contributions of this survey um, is that they give like here. So one, they give a good like taxonomy of RL environments. The second is that they talk about the limitations of procedurally generated environments. Uh, and the third thing is they talk about like limitations uh, of current RL research and ideas that they feel are underexplored. And so this is what motivated my tweet saying like maybe this gives like a good roadmap for people interested in exploring some of these problems. Um, and they also explore context efficiency and working in continual RL settings, right? So the continual RL setting is you just have this agent working forever, right? Not like just trained and then inferred. It's just like a system, right? So this is like, or as a product, the system or a product. All right. So they do mention that there's like a couple of more surveys, like on I don't know, like I mean, obviously RL is a deep field from like I don't know, curriculum learning to sim to real, probably somewhere by the same authors. I wouldn't be too surprised. Um, but yeah, I mean, at a high level, let's just go over the main terminology, right? So we've been using this term. So uh, Serdar is saying my current approach with dealing with vandalized signs is to check the HD map data and aux camera data to see if it's able to safe stop, to see if it's safe to treat as a stop sign, trying to figure out a better approach. I mean, so another approach would be you put like robots in the car, and then maybe in that case, like getting like the cost of a mistake isn't like as big a deal. So like we could put that like under unethical ideas for how to make like sim to real work. I think that's probably literally the plot of Blade Runner, if I'm not mistaken. So anyway, so what's the generalization gap, right? So we've been using this term generalization, and it basically it's this complicated looking formula, but it's actually very simple. So you can imagine that you're going to have a loss for some model on some data, right? And this data is drawn from some distribution. So there's going to be, because it's a distribution, you want to take an expected value of that loss over that distribution. So the difference between that expectation for the test versus the training loss is your generalization gap. So if you're used to something like just like, I mean, like again, if this is hard, like let's say you're doing supervised learning, then this will just be the two loss functions, right? But if you're doing some sort of probabilistic supervised learning, then that's where the expectation would come in. So here, the D test would be your mechanism of creating an environment. So either it's a probabilistic environment like ProcGen, or it's a function that picks environments for you. And XY is the actual environment. And, phi is basically just your model. But really, when we talk about generalization, there's also lots of nice properties that we would like to have. So one, we want it to be easy to combine stuff. So we want things to be compositional, as in the model works beyond the data that it's seen, that you can substitute some components, uh, that the composition doesn't have like global changes, as in if you change a sub part, it's not going to drastically affect some unrelated part. Like if you change your language module, it doesn't completely change your vision module, at least ideally. And that the model like is good at like paying attention to exceptions, like for example like vandalized data. um so the way all of these problems are encoded is what's called like a Markov decision process. So what that is basically you like so first off, like the goal of a Markov decision process, or at least the goal of reinforcement learning, is to given to maximize like the reward like within an environment, right? So this is like this reward function, and then P is a policy. So and it's a policy over some initial state, and then right? So that's generally going to generate like a new state for you. So generally going to generate a whole sequence of states, and this is where you get like the main equation for RL here, which is ultimately you want to sort of like do this like sort of dynamic programming where iteratively you have like some state that you're in. You want to pick like the and then you're going to have like a whole like sequence of actions that you want to make, and you want to maximize like long-term reward or like reward given like some like horizon function. I forget what it's called, like the symbol that looks like this. Um, so they do propose a variant here where like this is sort of like they're like, again like what I described before, like with hand waving in English, is still will give you the correct intuition. But they also introduce like contextual like Markov decision processes, and the difference here is that you have a Markov process where you can basically pick an environment, right? So basically, imagine action one is pick an environment, action two is give the agent a state from that environment, and then now if action one could be distribution, then you sort of get back to a formalism for how you could have identically distributed RL environments or completely out of distribution RL environments. But again, moving away from treating the training and testing data as being the exact same thing like we traditionally do in reinforcement learning. So just quickly, maybe I'll just quickly show you this. Um, so a Markov decision process is really like this sort of graph here, right? So where you're going to basically have like some states and then some probability of moving to some other states. Uh, the problem is with reinforcement learning, you don't know what this thing looks like, right? So you're trying to infer what this thing looks like, but at least like the environment is going to tell you concretely some signals along the way. Like let's say you're playing Mario, like as long as you're not dead, that's good. As long as your score is going up, you're collecting coins, that's good. Because also, by the way, in Mario, coins are arranged in such a way to make it easy for you to figure out where to go next. So they tend to be pretty good signals of what to do. But again, like the problem with these things is that the reason why we then call them like partially observed environments is that we may not know what the full MDP looks like, and we may not even know like what state we're actually in. Like all we have is like a reward function is that we sort of have to infer where we are along this process. Anyway, yeah, back to the paper. Uh, yeah. So basically, then they can like reformulate the generalization gap of a given. I would imagine pi is like a policy. So I'm excited for competition next summer. Glad to see SAE auto drive still going. I haven't heard of that competition, but if you could give people in chat some more information about it, that'd be great. I'm sure people would appreciate it. Um, so sure. So yeah, so like I suggested, the reason this formalism is sort of nice is that we can just provide like a concrete set of equations to be able to describe one like identically distributed environments like procedural generation. Sim to real is not that. Like sim to real is basically their testing distribution doesn't look like your training distribution at all. So this is completely different. So yeah, like you have like the reality distribution and you have the uh you have the simulation distribution. Even then the reality distribution may change over time. Like let's say your sensors degrade over time, or lighting conditions change, or the owner of the robot changed, or whatever. um so there's a whole bunch of stuff that you need to consider with stuff changing. They also briefly talk about healthcare, although I don't think they elaborate too much on this point in this paper. But you can think of like, let's say as a doctor, like when you're diagnosing a patient, like let's say you ask them questions and then they're going to answer those questions. And then based on those answers, like, oh, like, are you in pain? Like, yes, I'm in pain. Like, oh, how much pain? Like, oh, it's a 9. Oh, okay. So now you immediately know, okay, maybe like a leg is broken. Maybe this person's getting a heart attack or whatever. Like it's something serious. Versus if they say, like, no, it doesn't hurt. Well, you wonder, well, maybe nothing's wrong with them. Like maybe they just like slept bad. Maybe they're having a bad day. Maybe they're out of shape or whatever. So and then you'd ask another question to get clarity, and eventually we would find like the actual diagnosis, and maybe you'd even make an intervention. So you say, take this medicine, you should rest in bed, and then the sequence of decisions like that isn't just like limited to a single interaction with the doctor. It takes like several visits for you to actually figure out what to do next. So obviously, doctor visits are also like much costlier because if a doctor makes a mistake, like someone's life is at stake, so you don't want like totally random policies. But this is like again like back to the Tesla case. Like if a robot is trying to predict what a doctor is going to say, and then a doctor says stuff like, well, they're going to just go ahead and do their job, and then by function of like just your RL bot being valuable enough to just have the doctor have it inside the operating room or whatever, or the diagnosis room, the bot would get better. So they also talk about like RL here, even though like I already talked about this Tesla example, so I'm not going to repeat this again. Let's see here. Assumes block structure, a block MDP. I wasn't sure what this actually meant. What's a block MDP? I think this is a theoretical result, but let's just quickly Google it. Block MDP. So families of environment with a shared latent space and dynamics over that latent space with varying observations. Oh, I see. So maybe it's like a different simulation environment, but you would still observe things in the same way, as in it's still like, let's say, a Mujoko environment. So this is my prediction. Like I didn't read the paper, so please don't hate on me if this is incorrect. Let's see here. So one interesting thing they mention here is like metrics for generalization, right? So as in, there are two obvious ways of evaluating like generalization performance. So one is to look at absolute performance on evaluation tasks. So like let's say you just swap in environments and you're like, okay, how well did you perform? Sum all of those up. And the other is to look at the generalization gap, right? And I believe probably most papers would probably do the former rather than the latter. Yeah. Metric, track progress. All right. So yeah, I guess really what they're saying here is that it's just hard to describe a metric that would describe what generalization is in these cases. But if you could like potentially formulate like a function like that, or learn it, then like that could potentially be like one way of like at least knowing like what are we trying to do, right? Like what is the goal here? Uh, so there's really two angles that they describe. So one is increasing the training time performance while keeping the generalization gap constant, or decreasing the generalization gap while keeping the training time reward constant. Uh, so again, so here what you're trying to do is you're trying to control for one factor while improving for the other, because you want to be able to measure the generalization gap explicitly. Um, yeah. So let's see. And then they also briefly talk about like motivating zero shot policy transfer. I think they describe it as a useful problem, but it's hard. So maybe most times you'll just like end up relaxing this assumption to do anything productive in this area. So then they talk about a whole bunch of environments, right? So this is like a whole like page worth of environments. Like, and like, I mean, there's some. Let's see, what have I heard of? I've heard of Carla. I've heard of like mini hack. I've heard, okay, like I don't know, not noisy Mujoko. Like I've heard of RL bench, and those are pretty much like what I've heard of. And the way so one, they describe them. So there's just the style of game. So is this a 3D game? Is this a grid game or whatever? The context, as in, does this include procedural content generation? Are the environments discrete or continuous? And then are they ordinal, as in does the order matter? So that's what discrete O is. And then they also describe here the variations. I remember, what does this mean? So as respectively state, dynamics, observation, and reward function variation. Oh, I see. So do these environments let you vary the dynamics of an environment? So for example, can you change like the gravitational constant? Can you change what you're observing? Can you change the reward function? And can you change like the world in some meaningful way? Uh, right. So these are all like different ways of varying something. So the ways you may have heard about varying stuff is like, let's say, domain randomization, where you may want to change the colors or lighting of an environment. So that would, I would guess, fall under like observation. State would be you want to vary the location of starting objects. Dynamics is change gravitational constant. And then reward function is like, well, something like curriculum learning. So initially your goal is to get over this environment, but then then you may have two goals. So there's two reward functions that you need to optimize or whatever. Uh, So this is like just like I like this because it helps you think about, even if you want to create a new kind of RL environment, like where should you slot in your contributions, right? So this is all of this. So we talk about styles and environments. Okay, so what is this? So in purely procedurally conjugate environments, the only meaningful factor of generate variation is efficiency restriction. So we have no control of the factors of variation apart from sampling random seeds. The only choice we have is how many contexts were used for training. Okay, so in procedure content generation, you're gonna decide, okay, I'm gonna have like one of like 20 seeds, right? And then each of those 20 seeds is gonna create something. So the only thing that's really within your control is how many seeds to have and like the randomization algorithm. But like, do you know like which specific random instantiation is easier or harder? Like, which one should you show? Can you make like one environment more difficult in one aspect but the other? Not really, right? So this is, I guess, really the point is not that randomization is bad, is that procedurally generated procedural content generation is just like this like giant hammer that you're hitting a problem with. And so I would figure, and I forget if they mentioned this explicitly, but sort of either progressively making stuff more difficult or being able to decide what to make more difficult would be a much more meaningful way of achieving uh, generalization. Let's see here, training content distribution, a convex training set with full content. Okay, yeah. So they are explicitly mentioning this so that you may want to have like controllable environment validation protocol evaluation protocols. Yeah. So again, so this is, remember, like there's a context where you vary, let's say, friction and gravity strength, and during training they have it set to these values, like 0.5 and 1, uh, and then they do it vice versa for tests. Like how well does your agent do? So these tests evaluate its ability to exhibit productivity. Okay, so this gets back, I think, to this these categorizations they had here. So they're saying if we want to sort of um, like if we want to sort of figure out on which aspect of generalization are we targeting, it's helpful to say, is it like one of these things, right? Like is it something that we can, and I'm sure like people may have different definitions for these, like maybe someone will write some proof as to why all of these are impossible or you can only have three, and they'll call it some sort of maybe like the Zhang impossibility theorem or something like that. But regardless, I mean, like there's like these seem reasonable things that we expect generalizable agents to do. And so if we have an environment that is randomizing something, it helps to decide a lot like which one of those things do we think it will help in. All right. So here, for example, they talk about like non-visual generalization. So for example, if colors don't matter in an environment, maybe you can just make everything grayscale. Control suite variants, like if someone knows how to like grab cups, they'll probably know how to push a cup as well. So that's also unintentional generalization. Oh, what is this? Interesting. Okay, so they also mention here, like let's say people may have created generalization environments without that purpose. So like let's say the Atari developers may have never thought about even their games used for reinforcement learning. And then the people creating the Atari environment didn't intend it for generalization. But if you just like, let's say, one, pick an environment, two, train an agent on that environment, that's a way of potentially generalizing the behavior beyond just like a single game. Although there's still a point to be made, like maybe you're just like overfitting on all 10 games at once. So maybe that's possible. Uh, Okay, interesting. So they're saying, for example, systematicity can be evaluated using multidimensional context set and testing on novel combinations. So if you're doing new things. So productivity can be evaluated with ordinal or continuous factors. So for example, either you're dealing with like new angles or new classes that you haven't seen before. Did they talk about the other ones? Yeah. But they do mention here this again. So PCG benchmarks are testing for a general form of kind of generalization. but do not enable more targeted evaluation of specific types of generalizations. This means making research progress on specific problems is difficult, as focusing on the specific bottleneck in isolation is hard. And so I think there's a few aspects to this. I think one, environments that test out unique kinds of skills, making them progressively more difficult, and trying to figure out, like, within that context of that environment, like, what does generalization really mean? Okay. Right. Okay. So I think I apologize for going all over the place, because I just like read this paper right before stream, so a lot of the ideas are fresh. But so how do you like generalize an RL, right? So the most famous way, I mean, arguably, I mean, the way I knew about before reading this paper was data augmentation, domain randomization. Oh, thank you for the subscribe. I appreciate it. Uh, so one way, for example, is to make the either, like, let's say, like add more like metadata. So this could be, like, let's say, user labels. It could be a training time, doing some interesting stuff to your data. Domain randomization is a lot more. It makes a lot more sense. But the main idea there is that maybe you want to change the colors, maybe you want to change the location of stuff, maybe you want to add some like random noise to like someone's visual field or something. So these are all examples of domain randomization, even though they're arguably also examples of data augmentation. Like, let's say at training time, I just add random noise to your visual field all the time. To me, that sounds like data augmentation. Uh, and yeah, so this is the way they set them up. So this is sort of a summary. Uh, Optimization objectives would be changing the goals. So here, let's go here. Where was it? Optimization. Where is optimization objectives? That's environment generation. Where did they go next? Okay, okay, sorry. We're going in the right order. Um, yeah. So I think with environment generation, we have stuff like procedural content generation. And so it looks like people have done stuff like unsupervised environment design, uh, environment generation, domain randomization. Yeah. Uh, yeah. So, okay. So we talked about this a bunch, but just like basically ways of creating new environments. Um, Implicitly changing the optimization objective, procedural. Okay. So, for example, even something like zero shot reinforcement learning is something where you're completely changing the objective. But even changing the game is also a form of changing the distribution over which the training objective is calculated. So, this is this line here. And so you could also think of it as normalizing over a different distribution. But again, they feel anecdotally, I mean, they feel a bit similar to environment generation so far. But maybe I think they mean something different. Where here they're talking about how to pick environments and how to evaluate your effectiveness over them. And here, what they mean is how do you generate those environments in the first place? All right. So another theory, even though I'm not sure this is going to be the way to go, is encoding more inductive biases. So, for example, let's say you want the internal representations to be more consistent within an episode. So, add a cap on how quickly the representations can change. Maybe it's like giving the model access to some uh, like dynamical systems, like equations, right? So they could do some physics briefly. Maybe it's a model of how other people behave. I think, though, the challenge with this line of research seems to be that because uh, deep learning does really well with like very little biases, at least that's what like attention networks have shown us. That maybe you don't really need this, and I guess like they do mention attention agents here. So maybe, yeah. So basically, you make an agent attend to a certain part of the input, and then that can help it decide a bit better. But again, like attention in RL is very like very popular at this point, right? So you could have like the actual state, like basically a sequence of states, make them a sequence, put an attention like model on top of it, it'll work fine. You could have the attention be like a filter. Regardless, like attention is probably like gonna be like I would imagine a useful trick, if anything, because we know it scales. Uh, Others are basically regularization and simplicity. So basically, L2 weight decay, so having less complicated models, like using dropout. So these are all tricks you may have heard already, if you're doing like vision or language models or really any kind of deep learning. So I'd imagine uh, this is going to be very very similar. Learning invariances. So this is interesting. So basically, learning like representations or learning things that don't change. So they give an interesting example here. Uh, yeah. So basically, like again, like let's say you have like, imagine that you have like a multi-layer model that you're training. Let me draw a picture. Uh, and then this is, for example, like this is layer one, this is layer two, this is layer three. Maybe you freeze layer one, uh, and only fine tune layer two and three. And the idea would be layer one would hold some higher level representations that would help you play an arbitrary game or help you do well in an arbitrary physical simulator. So this is really, I believe, like what they mean by learned features, but I could be wrong. They may could be talking about something else here. I think they're probably also going to talk about things like contrastive learning. So basically, learn a good representation by guessing what that representation would be, and then based on the real world. So like basically, like think things like autoencoders, right? Like build an efficient representation, then figure out how useful it is. And then I guess like one way it seems like, and they pitch this heavily actually in the abstract even. So is to adapt online to the testing context. So use a hard-coded adaptation function. Okay. So they're really saying here, so this is again, I think another example of encoding some bias where you have an adaptation function. So a function that decides which agent should you use. So almost like a switching network or like a switch that's learned. It's like, oh, am I playing like am I right now working? Am I right now like having fun? Am I right now playing chess? Like I switch into a different part of my brain that does something. So I would imagine this sort of switching would also be pretty good using like some sort of like attention network. Yeah, I think they probably have like multi-headed architecture. There we are. Yeah, to basically learn one. Maybe you don't need to learn one. Maybe make everything fully connected and it works fine. I don't know, but it seems generally helpful. Maybe I guess to at least ask the agent, like, well, which environment are you in? Like, well, what's your task right now? And then once you've confirmed what that task is, like, then it can proceed. And people do this, right? Like, it's just if I'm like, let's say my boss asks me to do something, I go like, they're like, oh, could you please go like improve batch inferencing somewhere? And I may say, yeah, sure. Like, do you mean like fix the way error handling works in it? And then my boss will say yes, and then I'll go ahead and do that, right? Uh, Better optimization without overfitting. Uh, Basic policy gradient. Sure. I mean, better optimization algorithms. Although I think some version of the no free theorem lunch may say that maybe the optimization algorithms don't really matter. Maybe what really matters more is the way the environments are generated. Um, okay. Yeah. So this, I guess, is like to really conclude at this point. I think they talk about like there's maybe potentially alternative classifications that exist. That's great. I think this one is pretty good. Maybe there's another one we could potentially have for multi-agent RL. There's a lot of algorithms here. Um, okay. Yeah. So I think first off, this is something I've been excited about is that like because there aren't many like RL systems. So imagine something like a content recommender or a game that's being played on Twitch 24/7. Uh, that maybe the zero shot assumption is a bit too hard and it'll move to something closer to continual RL. I'm actually very bullish on this. Like I definitely agree that this will happen. Let's see. Something else they talk about is real world reinforcement learning generalization. So again, this is uh, oh, I see. So this is explicitly having benchmarks with a high cost for new samples and like under specified reward functions. So this is things like for example, here you'd have things like Minecraft, uh, high cost of new samples, like where like let's say so this is something like NetHack even I think is a bit like this. Like it's just expensive to do something. Um, Context efficiency, okay, sim to real offline RL. Uh, yeah, I mean, I think if sim to real is possible, then Tesla does not have a competitive advantage with self-driving cars. I think it's a big deal. It means someone like in their garage could basically build a better self-driving car algorithm, and it can be open source, and it doesn't have to be locked behind some like walled garden that is Tesla. So I think that would generally be a good thing. Reward function variation, I think, like, so I've mentioned this in one of my blog posts, where like reinforcement learning is a very declarative paradigm, as in you can sort of say this is the goal that I want you to have. But you know, like you can change it, right? So you can say, well, hey, like right now I want you to maximize the score, but like, hey, right now I want you to maximize the new kinds of environments that you're saying, or right now I want you to like basically maximize the amount of change in your own state function, or whatever. So you could encode all sorts of interesting reward functions, and definitely having environments that encourage that would be very helpful. And I see here, so multi-dimensional evaluation of multi-dimensional evaluation of generalization. So multiple different contexts, multiple different radar plots. Interesting, yeah. So basically, so like your tech tree, right? So this is like your agility, strength, etc. So like a star of like, you know, like are you good on this skill or that skill or this skill or whatever. So and basically plotting like people's ability to generalize across multiple dimensions, like language, vision, etc., and plotting them in radar plots. Let me just quickly show you what radar plots look like. Yeah, so these are used like, let's say, in like Dota skill, like how quickly do you learn new things, like what's your hero variety or whatever. So I'd imagine like a similar idea to work pretty well here. Sorry about that. So let's going back here. Tackling stronger forms of variation. So as in like just change a lot more crazy stuff in simulations. Yes. Yeah. So I think the TLDR seems to be like having like longer episodes with like online adaptation. So really this is saying like RL needs to move to systems, right? Great. So in conclusion, and if you stayed with me so far, thank you. Zero shot policy is useful, but we can relax it to like online environments. Purely PCG is not very useful because you can't choose what you're varying. Uh, for real world, we have to think about like sample and context efficiency. So basically, thinking about like environments that, like how to measure the evaluation of algorithms that do well in various environments. Uh, Dynamics variation is only tackled in limited settings, even though I think this is probably an easy problem actually to solve with like physics simulators. For stronger forms of problem, they're saying stronger inductive biases are necessary. You know, maybe that's true, maybe it isn't. I don't know. Or maybe we need like maybe RL doesn't really work well, and we need like model-based RL, like environment generalization, fast online adaptation, or whatever. So again, the bitter lesson to me by Sutton seems to be probably true, as in maybe scale is what matters the most. But to really measure whether that's true or not, you actually need data sets to keep up, right? So we need online data sets that are continual. And zero shot seems to be kind of like an unfair version of that. Like it's just not fair that if you've never seen something before that you're expected to do well on it. So how do you create data sets that do give you that possibility, whether it's things like in Unity where you can change your own environment. So basically Unity, let me write this down. So let me write this down here. Unity change. Right? So again, folks, I hope this was helpful, and thank you to everyone who's been yeah, so thank you for everyone who's hung around for this long. So I hope this was fun, and if it was, please make sure to like and subscribe. It lets me know whether this content was useful. Also, make sure to join the Robot Overlords Discord channel. Like I hang around there quite a bit, and so I can answer any questions you may have there. Uh, as far as like what to expect for other streams, like so right now I'm pretty busy with preparing a talk for the AWS reInvent conference and talking about like my day job, which is figuring out like how to scale PyTorch and tools to do it better. So talking about TorchServe, TorchX, a lot of new stuff that's happening in the distributed realm. So I have quite a bit of projects that I'm finishing up in both projects at this point. And so that's actually why I've been kind of quiet with streaming and blogging recently, because I have like some like real projects that I really want to finish up that I think a lot of you will be excited about. So yeah, like I said, if you have any other content suggestion ideas, feel free to let me know. And like always, like thank you so much. It really means a lot that you watch this. Thank you.